the effects of interventions related to one disease, how that on patients of another disease. Okay. So this is very preliminary work. Is the first time we are presenting these results. It's the first time we have a very crude first draft with initial results. Is definitely a preliminary results. So it's actually a great point for us to try to tell our storyline and get some feedback. So I was talking to Philippe, right? Philippe, if we don't have a big group here, so if you have a comment or a question, then maybe just unmute yourself and let's just have a chat about it. And that is probably the more productive way to go about this. Anyway, so let me get going. Let me just get. All right, so the impacts of disease-specific shocks or policy interventions, they're often measured based on variations on patients of that disease or something related to that disease, right? But of course, policies that target one disease can have spillover effects into morbidity or mortality of another disease. And hold on, because I got the wrong presentation here, guys, my bad. I lost my presentation. Oh, here you go. I'm sorry. Sorry about that. This is a bit shorter. So like I was saying, policies that target one disease can generate important spillovers on the mortality and morbidity of another disease. And here just have a few examples. I'm just to make this literature review quicker in this version of the presentation. So this is an examples mainly from Africa literature that looks at anti-malaria policy actually reduces competing mortality risks. We can have behavioral channels that show that patients change the way they approach investments in other types of disease. So here we have some evidence that spillover effects can go from one disease to another disease. In this other paper here is another example of a dewarming program that was applied to children in certain schools. And then they show that children that were not treated either within the school or in other neighboring schools, they also benefited from the program in terms of health outcomes and also in terms of educational outcomes. So in the first one, I have disease spillover into another disease. And the second one, and it's an example of how I intervened the program related to focusing one target population and spillovers to other individuals, right? Going to other individuals, they spill over. So these are kind of examples of positive spillovers. There are also some evidence out there of negative spillovers coming from the HIV literature in Africa as well, showing that HIV-specific investments, like when you have like this huge wave of investment that can actually crowd out non-HIV resources. So it can attract doctors to change sectors and from non-HIV to HIV, and that can cause short-term kind of increase in all-cause mortality, things like that. So either behavioral, from the behavioral side, more like the health demand side, or from a health production side, spillovers are possible. What's going to be our contribution to this literature is to kind of think more seriously about nonlinearities, because all these papers that I presented to you, they base their conclusion on linear models. And our take in this paper is that when we're modeling a health outcome, it's very important to look at nonlinearities. Like we know, for instance, that from the environmental literature, for instance, we know that there are significantly nonlinearity effects of pollution on health, right? And here I'm going to show you just now an example of important nonlinear effects related to COVID-19 outcomes. Okay, let me just show you this one graph. So this is a recent paper from Nature that looks at immune response after the first dose of Pfizer, the Pfizer COVID vaccine, by age. So I'm pretty much looking at what's the immune response by age, and can clearly see here that there's a nonlinear effect. Okay, so this is new evidence of this nonlinear effect on immune response by age. So of course, if I'm studying, let's say in this case, a COVID-19 outcome, and I want to study how that relates to age, using a linear model is going to give me very biased estimates of marginal effects of how age influence the severity of my COVID-19. And this is only, like, I'm just showing this a little bit of evidence from one kind of channel, right, which is immunity. And there are lots of literature out there talking about nonlinearities in health. So that's what we're gonna be the focus of this paper. We're gonna contribute to this literature by kind of developing a model that accounts for these nonlinearities. And we're gonna apply our model to examine how the COVID-19 pandemic affects non-COVID patients. Okay, so that's the research question. So now let me show you like the model that we are trying to estimate. And it's a model that we think it's very interesting because it has the simplicity of a parametric model, but it adds that flexibility to account for these nonlinearities that we are seeing that are going to be very, very important in modeling a health outcome. So it's a model that was first proposed back in the 80s as a classic semi-parametric model, if you think of the first equation. So we have an outcome that is a function of policy variable or a variable of interest. Here, I'm going to, in this first draft of this paper, we're going to simply use a pandemic indicator. So before and after the pandemic, and we're going to estimate a hospital level model. So there's going to be variation when the hospital is affected and which hospitals are affected. And I'll talk more about our application in the second part of the presentation. But this could be, this doesn't need to be necessarily a discrete variable. This could be some measure of the intensity of the pandemic as well, like capacity of the hospital, something like that, related to the pandemic. So I have this parametric form, and we have a non-parametric portion, a very flexible portion that we make no assumptions on the shape of the relationship between characteristics of the determinants of health outcome. That could be, for instance, patient characteristics or hospital characteristics on Y. So our claim is that it's very important to control for these nonlinearities because they are a big deal in health, in modeling health outcomes. Okay. So in this model is a model, the model with these two equations in being explicit about a second equation is a model that was proposed by Chernozhukov and co-authors, and they are explicitly modeling how the probability of being exposed to a pandemic is explicitly modeled in this model by the second equation. Okay, so in this sense, this X set of variables can be considered confounders because they determine both health outcomes and the probability that you're going to be affected by the pandemic or the intensity of the pandemic. Okay, we note here that this M function, that is the flexible function that we're showing no shape for, that would disappear if I had an experimental paper, right? Like a fully randomized study, allocation of treatment would be completely random, right? So this M would go to 0 and our treatment would be completely exogenous, independent of X. But in this paper, we are in this model, we are saying that we need to have X there in order to control for that selectivity effect, okay? So the focus, if you see, like the focus here, like this X and this G function are really what the literature call nuisance parameters, right? So they're not the focus of the research question. The focus of the research question, the main parameter of interest is this tau. And again, one of the reasons we like this model is that this tau is it's clear, like the parametric effect, like assumed to be this way, the difference in means of health outcomes free from this nonlinear confounding effects, right? So if I put this G to the other side, I have Y minus G. That is a function of the pandemic. It's pretty much. Once I control for that, I can just see what's the effect of that modified health outcome on the pandemic in this very simple parametric way, intuitive, with a lot of, I would argue, a lot of policy variable, policy contribution importance, right? The interesting thing here is that in this model, if you don't, let's say so these errors are exogenous in this thing. So we have a story here of selection based on observables, but if I don't know this G function, maybe I can just ignore it, right? And then run the model. Then we would have clearly a problem of omitted variable bias, right? Because this X is correlated to C. Okay, it's actually explicitly in the second equation, right? The interesting thing here is that the omitted variable, and in this model, and again, this is a very, I'm spending some time talking about this because I'm gonna add what's going to be the challenge in a second. But the interesting thing here is that this omitted variable bias essentially is a if I didn't have that X and want to get away from it, essentially it's a misspecification problem, okay? Because if I knew G, if we somehow knew G, we could evaluate the G function in our data, put that information here, get that out of the error, and OLS here would be fine, right? Okay, so that's what we have, but we don't know G, and also misspecifying G, we go into the literature that motivates nonparametric econometrics that this is going to be biased, and so on. So, given what I just said, an approach to estimate this style could be, okay, what about, I'm going to include X and C in my estimation, and I'm going to try to use approaches to estimate G, like in a traditional semi-parametric approach, like the one proposed by Robinson, and go with it. The problem that is going to be the key challenge that here is kind of the methodological innovation that Chernozhukov and co-authors talk about, and this is everything that I'm kind of saying is going to be based on their model and their contribution to solve this problem. The problem is that we are looking at a model where X is of a high dimension, very high dimension, right? And this is exactly the case when you're trying to estimate spillover effects based on hospital data. Just to give you I'm going to again talk about the application in a second, but just to give you an idea, we have data, hospital level data for hospitals in the state of Rio de Janeiro in Brazil. And we have information about, we'll look at ICU, intensive care unit outcomes, and we have information about the types of ICU in each hospital. So there are one of the models that we estimate is going to be a pediatric model, only for children. And there are only 28 hospitals in the state of Rio that have pediatric ICU units. So if I look at the cross-section variation of this model, it's only 28 observations. And then when I contrast, okay, so we're going to have panel data, we're going to have a panel model, and that's going to increase the number of observations, sure. But you see that I have a very little cross-section variation, and when I contrast that with the amount of information I need in this G function, the complexity of the G function, and all it's not only like that the number of variables that we need, but also the possible combinations of these variables. Like I could have age, I could have polynomials in age, it's possible that an interaction between, let's say, age and gender is very important to determine health outcomes, right? So this becomes really quickly a super high dimensionality problem. And the problem here is that standard non-parametric estimators have poor finite sample properties, right? And they will perform really badly on this kind of setting when I have a high dimensional parameter and I have a low dimensional parameter. Okay, actually, they'll perform really bad when I have a high dimensional parameter. I'm going to get to that second part next. All right, so the literature goes on. The literature, the nonparametric literature evolved a lot since this first model was proposed in the 80s. And there is now, you can think of this as a new generation of non-parametric techniques that is kind of branded as machine learning, right? And these estimators, they do much better in this kind of setting. They do much better, like rates of convergency, for instance, of kernel regressions compared to many machine learning estimators are much more favorable. So they have a much better finite sample properties than these traditional non-parameter estimators. Okay, so let's go and so the idea then is a kind of a logical step is let's use these tools to estimate a model like this. And again, well, if we're gonna use some sort of machine learning, there is really no need necessarily to focus on this second equation if I have the first one. So we can kind of focus on the first equation and try to estimate this model. And one approach to do this using like off-the-shelf machine learning algorithms, because a machine learning, off-the-shelf kind of machine learning approach is an approach to estimate the conditional mean of y, right, of a variable, okay? It's kind of like a basic off-the-shelf approach. Here, it's a little bit different because I have this semi-parametric structure, there's this structural model. So I have a general formula, but I have this parametric formula here. But one way to do this is not that hard to use machine learning to do this. We could use some sort of iterative approach like this. Okay, so what if we pick a guess of tau, okay? And then with a guess of tau, I can put this to the other side, right? Of the equation, calculate this y minus c tau variable based on my guess, and then use a machine learning to estimate how this modified health outcome fits on X. So that would be an estimate of the G function based on the guess tau hat. I can get that estimate in turn, do the same thing that I did before, subtract from my health outcome. So I have a health outcome free of the confounding, nonlinear confounded, then use a linear regression because then I have a linear relationship with C, get a better tau, go back to step 2, do the same thing again with this new tau, get the new G, go back to 3, and keep doing this back over and over and over until we find convergency, and that's our estimate of tau. So when tau converges, then we stop. This is an approach that leads to excellent prediction. This is an approach that is discussed by these guys. They lead to excellent prediction, but the estimates of tau are severely affected by regularization bias. So the bias of the regularization process, the stuff that goes into the machine learning algorithms to make that a good fit. In this setting where I have a high dimensional parameter here and a low dimensional parameter, bias the estimate of the low dimensional parameter, which is in this application the focus of the model, right? So it's almost like I have too much weight here and little weight here, that when I'm fitting this in an off-the-shelf kind of way, using something like this, I'm going to actually have biased estimates of tau. And this is a beautiful paper. They show this analytically in a very general way. So I'll refer you to that paper to show that. And then once they have that analytically, they have a procedure to correct that. And the procedure is called double Debiased or orthogonalized machine learning. Okay, so it's a procedure to use machine learning approaches to take advantage of this new generation of non-parametric tools that have better properties in high dimensions, but in this setting that I have high dimensionality of X, still estimate unbiased, consistent. We still got a consistent estimate of tau. The other interesting thing is that this estimate of tau is going to converge very quickly. It's going to actually have parametric convergence rates, and that's kind of a bonus of the approach. I'll come back to that a little bit later. Okay. So this is kind of just a picture that shows, like I said, they do that with analytically with theory, but they also provide simulation evidence that off the shelf, this kind of off the shelf approach that ignores this dimensionality and balance here will bias the estimate of the low dimension parameter. And this is what it is, right? So you can see that the kind of non-orthogonal typical machine learning approach to like this to get a tau will bias the estimate of tau. And if you correct with their orthogonalization procedure, we're going to talk in a second, we fix the problem. They show, again, this is simulation evidence, but they show that also analytically. Look at the simulations are running kind of a model that is pushing, like I have, this is the dimension of this matrix. In the simulation that I have 20 variables with 500 observations. And this is the performance that they're getting. Okay, so moving on, what is this orthogonalization procedure? So before we're talking about the double debiased machine learning, this orthogonalization, let's kind of think about orthogonalization in kind of a lot simpler context. Let's assume that the model is linear. And what is it? Just like to think about orthogonalization. So what is this? So then we can go back to our introductory econometric classes and think of the Frisch-Wall-Lavelle theorem of regression partition, and the idea that the fact that an estimate of the tau parameter in this linear model. Okay, so this is just like a detour to talk about orthogonalization. A linear model, the tau parameter can be estimated exactly, precisely. Analytically, you can show that an estimate of tau can be obtained with the following procedure. I get y and remove the effect of x. So a linear regression of y on x, collect the residualized y, the y free of x, right? Then I do a second step, and then I get a linear regression from c on x, okay? So I get c without the effect of x, collect these residuals. If I run a linear regression of the first residual and the second, that slope coefficient is exactly the same as this parameter, okay? So that is, if you open up an econometric book, they will show you all the matrix is actually not that bad. You go through the algebra and see this. Then we go back to so this is very old, right? I don't remember. This is very old. Then we go back to Robinson. Robinson in this semi-parametric model in the 80s, they're proposing a way to improve convergence rate of semi-parametric estimators by doing this type of orthogonalization. Again, removing the effect of x, which is the kind of the confound that affects outcome and selection, right? In this way. But what he proposed is kernel regression of y on x, because in his model, I want to go back, this is linear, right? In this model, the effect of x on y is nonlinear through g. So we are using kernel regression to predict y from x, collect residuals, kernel regression to predict c from x, collect residuals, and then you can do linear regression on residual, again, residual on residual regression, and that's going to recover tau, and that's going to have a convergence rate that is much faster than all the semi-parametric estimators that were based on kernel regressions in different ways, right? What Chernozhukov and co-authors kind of did is take this idea further to the setting that I have a high dimensional parameter and a low dimensional parameter in a model like this, okay? So the idea is to orthogonalize the model by using a machine learning algorithm to predict y from x, collect residuals, use a machine learning algorithm to predict c from x, collect residuals. Then you can do a residual regression, right? This is the kind of, I'm like orthogonalizing because I'm removing x, which is the confounding from y and c, and when I do the outcome and treatment, and when I do the residual regression, they show that we can recover tau. So it's interesting because it's super general that you can use your favorite machine learning algorithm on step 1, your favorite machine learning algorithm on step 2, and get an estimate. Okay. So this is kind of the general idea. The actual algorithm that we actually use and implement, they talk about, there's other things, this in itself generates some overfitting issues, that there's overfitting in this, right? Because that's why it's called double machine learning, by the way, right? Because you do machine learning twice in this fashion to orthogonalize the data. So they will, to address overfitting issues, they will do some sample splitting that I'm not talking about here, and cross-fitting software within machine learning, and go. The cool thing is that you end up, when you go through the math, a lot of things cancel out, and you end up with this root n consistency, kind of in this fashion, right? That Robinson, the name of this paper from Robinson is, I think it's root n consistent semi-parametric estimation. That's the name of the paper, right? That he's kind of proposing this, and they with this machine learning thing algorithm, they also achieve root n consistent, which is the key to improve. Also important to improve performance in finite samples. Okay, so this is the idea, and this is what you're going to implement to estimate this tau. So here is kind of a little bit more kind of us now applying these ideas. So what we're going to do is estimate this model like this, right? So Y in our model is going to be an outcome of non-COVID patients, of ICU patients, right? So of ICU I at month by year T. Okay, so it's a panel data model on I and T. I being the hospital ICU, and T being the month. The data goes from the beginning of 2019, January 2019, to the end of 2020. So this is, excuse me. So this is 24 months. And we're going to have 60 hospitals with adult ICUs, and in one model, I'm going to talk about that in a second. In another model, 28, like I said, 28 hospitals in the state of Rio, in our data, with pediatric ICUs. So this is a hospital level outcome. And you can see the dimensionality issue here is really important, because, and this is why we're kind of going towards this direction. If you are taking nonlinearity seriously, and you're really worried about misspecifying the effect of confounding, the confounders, right? And then you are trying to look at health outcomes, it's going to be really hard for you to have, especially with the pandemic, individual level information, panel data, right, for health outcomes. Like how many, like follow a patient over many time periods to have individual level panel data, individual level information that you can use like this. So you have more data, let's say. Well, that also would have, it is a different model, I understand that. But even if you wanted to do that model and you have some sort of identification strategy in your head, it would be really hard to get that data. What is available to us, and to, I would say most applications would be more like hospital level data. And then we end up with the situation, how many ICUs you have, right? How many ICUs you have in a state, right? How many hospitals you have in a state. So when you're trying to model something really complex. So that's why we think that having an approach that can handle this high dimensionality is really important. So the health outcomes we're going to use are mortality rate of ICUI month T, like hospital level mortality rate, ICU level mortality rate, and duration of stay, but just for surviving patients, because we don't want to have a situation that someone let's say went to ICU and had a very bad outcome really quickly, let's say doesn't survive the ICU, then that would not necessarily be a positive health outcome. We want to have clarity interpretation. So we can look at the surviving patients and look at duration of stay. And then if you're so conditional surviving, we want you to get out of the ICU as quickly as possible. So that would be like a positive health outcome. Okay, duration of stay. All right. So in this first version of the paper, we're just using a simple indicator for the pandemic. We also have detailed level on detailed data on when the pandemic got in each of these ICUs. Okay, we have that information, so we can have IT, right? We have variation in the cross section and in time on when the pandemic reached that hospital. Okay. Then I will have patient and ICU characteristics. I want to show that in more detail in a second. And another thing that we want to do is kind of throw in here, because it is true that we don't have a lot, at least not in this first version, we don't have a lot of patient characteristics, let's say, or hospital characteristics. But by having like a hospital fixed effect, so we think that hospital fixed effect is going to be really important, because it's going to capture all the unobserved time invariant effects characteristics of this hospital. We are going to throw that in the G function, and this is coming here with this kind of notation with a fixed effect. But to operationalize this, we actually throw in the dummies, right? So you can see that we're really pushing this model in terms of dimensionality, because I'm going to have dummies for, so it's about 28 hospitals, 27 dummies here for hospital fixed effects, and then time fixed effects. So 24 months, because I have all the months of 2019, 2020. So then you're going to have 23 more variables here. So you're really pushing this model with this kind of specification. But it is important to control for time fixed effects, because we're looking at a state, but there are national level COVID policies, okay? And there are state level COVID policies, things that will affect all the hospitals, that could affect all the hospitals in the same time period, right? So we have these common shocks that would be captured by something like this. And we are assuming that this could be nonlinear, right? It's going through this G function. So it's all in there. Yeah. And in terms of the steps, again, if you go back here, like you can use many algorithms to do this. Papers that apply this use the combinations of algorithms, because it may be the case that you, let's say, estimate a random forest here, and I don't know, some boosting algorithm here, and one algorithm is better to predict the first stage, the other one is better to predict the other one, so you can get a combination of algorithms to get these residuals and then run your residual regression, right? So for this preliminary results, we're only using forests, random forests, and that's how we're applying these steps. All right. So just a little overview, quick overview of the data before I show you the results. So this is what we have so far. So again, data is going to be a hospital level, or some hospitals will have separate ICUs for children, like pediatric ICUs and adult ICUs. So the outcome is at the ICU level. So this is actually, when you look at fixed effects, is actually ICU level fixed effects. But anyways, so I have 60 hospitals or 60 ICUs or hospitals with ICUs. There's adult ICUs. So you've got 60 hospital times 24 time periods. I get to my number of observations. That's 1,440, right? And this is just like simple table statistics. I'm pulling COVID patients and non-COVID patients together. You just got a sense. I mean, it would be more informative if I only looked at one type of patient than the other. But for instance, something we can see here is that we look at 21% of the observations in this model are post-pandemic observations as defined by the month that the first COVID-19 patient got to that hospital, right? So average age of a ICU adult ICU patient is almost 60 years old. I have this out of town variable that looks at the proportion of patients in the ICU that is from another municipality. And this can capture things like, some of these hospitals are hubs for rural areas. So we're capturing some of that effect here. Then we have ICU beds and ICU capacity. Right. So on average, these hospitals have 24 hospital beds and 70% capacity over the time period. So it'll be interesting actually to see before and after the pandemic. I don't have that data here. And then similar statistics for the pediatric. Okay, ICUs. You can see that mortality for pediatric ICUs, thank God, is much lower. Duration of stay on average 11 days for pediatric ICUs. This is the entire sample. Duration of stay for the adult ICU is 6 days, and this is duration of stay again only for patients that survive. I'm throwing the mortality out to calculate duration of stay for this data. Okay. So it might be one of the, I have to check why we're losing here 4 observations. So it might be that a small hospital, we didn't have patients that survive in a given month or something like that. I apologize, I don't know what this is at the moment. But you can also see that I just talk about hospital size. The fixed effect is going to be important, right? To kind of get at that. Okay, so now I'm going to show you the results. So again, the focus is on the tau parameter. Okay. So here, and we also had data on COVID patients. So we did for both non-COVID and COVID patients. Okay, so, and this is really the columns 1 and 2 is the spillover story, right? So just to have a reference here to baseline effects, I'm putting here pre-pandemic mortality averages, the average for, so first column is in mortality for adult patients. So before the pandemic, on average, 28% of patients survive ICU hospitalization. We estimate this and we find that the tau parameter is 0.048, highly significant, which says that let me just show the model again, just to be clear. Look, we're estimating this parameter here, tau, right? So this is the differentiated effect on health outcome, given that you are in the post-pandemic regime, right? So the pandemic increased mortality by 5 percentage points, and then to give you a reference from a baseline of 28% chance of mortality. So this would be 5 percentage points out of 28, would be roughly 17% increase, right, in mortality for non-COVID patients. So right there is a big result of the paper of this is a preliminary result. We'll talk about future work in a second, but it's a result that shows the spillover effect, right? This shows that there is something going on with non-COVID patients in ICUs after the pandemic. The risk of mortality is increasing by 5% in these ICUs. When you look at pediatric ICUs mortality, we really don't find a spillover effect, right? This is here with a 1 star, but the p-value of this is actually 0.098, so it's a very marginally significant, and the magnitude you can see that it's really small, 0.5 percentage point over a baseline of 8%. So this is, if there is a spillover effect, here is weak evidence of there is a spillover effect on mortality, of non-COVID patients. Then when you go to duration, average duration of stay for surviving patients in ICUs in Brazil is the average pre-pandemic is 6.5 days. This is measuring days. And after the pandemic reached those hospitals, you increase your duration of stay by almost a day, right? Interestingly, we do find a spillover effect in terms of duration for pediatric ICUs, right? The average length of stay was almost 12 days and increased by a little bit more than a day. So we can only, at this point, you can only speculate as for what are the mechanisms behind these effects, right? That's something that we have plans to look on. It might be that hospitals are pushing resources thin and have to make, challenging trade-offs between this type of patients. There is some sort of isolation, right, that we need. Especially in the beginning of the pandemic, there was a lot of uncertainty on how to treat a COVID-19 patient, and we got to think about these mechanisms. But this is what we find so far, and we did also for the COVID-19 patients. This is for non-COVID-19 patients, and of course, I don't have COVID-19. I don't have COVID-19 patients before the pandemic, by definition, right? Before the pandemic, there was no COVID. So the baseline here is a bit of a, I don't know if I can call this a synthetic control, or because the baseline, the control group, if you want to say, it's non-COVID patients. This is actually the same group as this one, right? The same control group as this regression. But here, I don't look at the COVID patients in the post-pandemic. And here is only the COVID patients in the post-pandemic. So the baseline, that's why I have like dots here, because the pre-pandemic baseline mortality is what is the pre-pandemic baseline mortality, 28%. But you can see that the mortality, like if you are a COVID-19 patient, your risk basically doubles. Your ICU, if you are a COVID-19 ICU patient, your risk basically doubles if you are a patient in Brazil, according to these estimates. Your mortality risk, because it goes from 28 to 28 plus 23, 50%, 51%, right? Almost 51%, right? So it's a huge increase in risk mortality that COVID brought in this. And this is before variants of concern, right? Because this is basically Brazil's first wave. Was kind of maybe the beginning of the second wave was catching here at the end of 2020, but it's basically before variants of concern. This is before kind of Delta, for instance. And that's probably why we don't really find an effect on the pandemic or on the mortality of pediatric ICU patients. Yeah, we don't like that this effect is negative, because it's kind of saying that the pandemic is decreasing the probability of mortality. But this this is like the p-value here is like a point is 0.97 98 again. Like it's very weak evidence. So I don't know. I wouldn't put much effort in this. I mean, much weight on this negative sign. We have a little bit more evidence that it delayed the duration of stay for COVID patients in pediatric ICUs more than kind of did for non-COVID patient pediatric ICUs. And duration of stay for COVID patients increased by almost 3 days compared to baseline of 6.5 days. So anyways, this is what we have thus far. Let's talk about some future work. Well, what we want to do, like we kind of just got our hands into this, and then we're, developing codes to do that orthogonalization and all that stuff. And we just did one machine learn application, right? Which was the random forest, because it was also, I think it was, I may be wrong, but it might be the model that in their application, when they applied this, they had one of the best results. Don't quote me on that one though. but we definitely need to refine our machine learning estimation. And, for instance, we never checked. Here, I didn't offer you any discussion on the choices of hyperparameters of the machine learning model, right? So we just kind of use the default of our library and went with it for this first round of results. We definitely should think how the choices of the like in our case, the forest and the hyperparameters of the forest model. Yeah, go ahead.
Sven has a question. Sven, can you ask your question? We are almost at the end, so.
Yeah. I was going to ask, is this the end?
It's almost the end.
Yeah, this is the end. I'm just going to talk a little bit about this, but. Oh, okay. Can you ask later? Okay. So, anyways, I mean, there are new algorithms out there, boosting algorithms that we should definitely try. And there is also the old kind of generation of the first generation of machine learning algorithms that is also be interesting to see what happens to tau with these different algorithms to estimate this step. And like I said before, the combination of them, because you could have one algorithm could be best for orthogonalizing, right? The first step, the other algorithm could be best orthogonalizing the second step of orthogonalization, Y and C. And it would be interesting to see the sensitivity of the low dimension parameter, the tau, to this stuff. We also I think we have more data that we can use, like race. Again, like I said, this is a very preliminary set of observables, which is going to be really important to have a good model there, because all that I told to you is based on this idea that I have errors that are exogenous condition on these observables, right? So that's going to be very important to think really hard about this. I think that, for the pandemic, maybe at the hospital level for the pandemic, we can make the case that, if we carefully define that model, we can make the case that we have good models. We never use polynomials. You should probably use polynomials and combinations of things in the model. Our machine learning is not generating this automatically or anything. Another thing is that if you look at the data that we actually have, we are using like for instance, for age, we are using average age, right? Average age of the patients. What we have is we have to characterize patient profile, right? And we're using averages to characterize the patient profile of the ICU. But it's possible that other moments of the distribution of patients in that ICU can affect health outcomes, right? So it's possible that an ICU that has a high variance of age, that variance of age may influence mortality on that ICU. So there's a lot that we can do, and then there are combinations and stuff. And then again, we also plan, this is kind of stuff we're doing now. We're planning on investigating also some of these mechanisms, see if we can find some evidence how are these spillovers coming through, if let's say the supply of doctors on these ICUs are changing, for instance. That would be one possible mechanism to generate these spillover effects. Anyways, I'm going to stop here. Thank you very much. Now it's time for...
We have a question, I think. Ben?
Yeah, I'm going to play the grumpy guy role. Bruno, this was very technical and probably very interesting, methodologically speaking, how to address a problem set that previously has not been satisfactorily addressed. But why are you doing this? And who cares about what you're doing? And can you actually measure the benefit of applying machine learning over the alternative, like sticking with the old approach? Can you quantify the benefit you're getting from that?
So to start with that last question, under the setting that we have, there is I don't know of an alternative, right? So I could estimate a linear model, but a comparison of this estimate with a linear estimate, maybe that's interesting, but that's theoretically wrong, right? So kind of that is kind of my answer. I think there is a lot of sensitivity that we should do and we have to do based on this stuff. like how to address, how to implement the double machine learning. There's a lot of stuff there that we need to do, but the entire kind of my motivation was pretty much saying, like, how do we estimate this when you have this particular type of problem, right? So if you have another approach to estimate this model, given our challenges, then I'm all ears, of course. So that's kind of the second part of your answer. The first question is, why do we care? Well, there's a big literature on spillover. I only kind of did 3 bullet points in the first slide, right? On that, if we are able to, first, I don't know of papers out there that take a serious attempt of estimating non-COVID spillovers to non-COVID-19 patients. There's a lot of evidence and stuff that are less sophisticated than this, that suggesting that there is a big effect on other types of patients. But I think this is kind of more sophisticated in the sense that we're really trying to get at a causal effect, including these nonlinearities. And here, once we establish that there is an effect, look, the policy implication is there is, after the pandemic, we increased mortality of non-COVID patients by 5%, then we're going to go, okay, why? This is what we want to know now. Why? If we can learn why this is happening, then we can try to mitigate these negative spillover effects, right? So that's kind of the big policy implication.
Thank you.
Shaoli?
Yes, so it's kind of very interesting. In your model, is say a binary variable? Is it a dummy variable? I'm wondering.
This one, yes, yeah.
Because you talked about like waves, right? So if you have the number of COVID cases, I don't know if you can have that in your model. And is there a way kind of to include that?
No, for sure. Yeah, that's right. So here we have just that kind of separating the outcomes into 2 parts, right? Pre-pandemic, after pandemic, based on that hospital level variation. So we don't have kind of this intensive margin interpretation of this thing, like the waves, but we get a little bit at that. So it's a bit of what kind of question you want to answer, but if you are concerned about how that affects this estimate, my response to that right now would be that we do have hospital capacity as a control, right? Hospital capacity, hospital beds as a control. You just gave me a great idea. I don't have, okay, this is a great idea now. I just had, I don't have, when I estimate this model, I have non-COVID ICU beds in the model, but I could put from the other ICU, right? I could put the ICU, COVID ICU capacity as a variable in the non-COVID model. That's an interesting idea, actually. But, or I could also, that's one thing, to try to control for the effect of the waves on this type of estimate that I'm separating the data into 2 parts, pre-post-COVID. But I agree that adding the intent, like the number of patients in the hospital, and see how the number of COVID patients affect outcomes of non-COVID patients, that would be really interesting too. And that's a different model that we can totally incorporate. And yeah, we should definitely do that. Thank you, Shaoli.
Mike?
Hey, Bruno, thanks. I don't really have anything methodologically because I'm not familiar with these models. So it's kind of along the same lines as Sven's question, I guess. Have you thought, I'm sure you have, but can you speak to kind of a very, let's say, ethically or morally wonky benefit cost analysis, looking at COVID patients taking up hospital space versus the cost of the additional deaths that you've calculated of people that are not getting in, and what that could mean, what that has meant, and what that could mean moving forward.
And I've been thinking, we are having conversations with my co-author about this. We've been thinking like, how can we kind of push this to the next level, right? And what we've been talking about now, and it's kind of beyond mechanisms at this point, right? Here's I don't have a well-structured answer in my head, so I'm gonna just put out there what I have now. So what might be behind this is, you can think of a model, like a micro-based model, right? That I have limited resources, I have this pandemic now, and I have to divide my resources in two ways. Like I have to put my resources into the COVID basket and put my resources into the non-COVID basket. And there's a whole bunch of implications there, right? Hospitals are making these decisions, right? And we are seeing the outcomes of the decisions here in this table. Is there a way for us to study what's the optimal decision level? Maybe that's what you are trying to get at. And we can maybe get a metric of the metric that is gonna cut across maybe mortality, right? So what if I wanted to minimize mortality? For me to get at that, we can kind of think of a micro model, and then you probably would need a bit more on the mechanisms, kind of what's the margins that we are adjusting to get at these results, right? But that's what I think this can become really interesting, right? And to kind of say, are the managerial decisions at the hospital level optimal or not in some sense? That's exactly kind of where you're reading exactly my mind, where we want to go.
Good luck with that, Bruno.
Is that more or less what you meant?
Yeah, that's what I was after. What's your gut feeling right now on this?
I have no idea, man.
All right. Okay.
I don't know. I think the point is not to. I think that one of the things that I wouldn't want to do is to be like, I don't know. It's not like to point fingers in a way, right? The point is like, look, there's all this uncertainty, and hospitals are doing their best to allocate these resources. Some hospitals are going to do a better job than other hospitals, right? So what is it that some hospitals do that is better than other hospitals, right? It's more like that. That's kind of how I would think about this.
Henry has a question.
Yeah, thanks. Quick question, and I'm not sure you can answer right now, Bruno, but the way you're sort of describing it, it seems as if you're treating the decision maker at the hospital level as somebody who sort of sees everything at once and then decides and allocates. But the reality is that it's sort of coming in one at a time, and there's a lot of sort of path dependency, right? Like if a whole bunch of COVID people come, that's going to lead to sort of different outcomes than if it was one COVID, non-COVID, one COVID. So is that a problem? And if it is, can you address it in any way with your data?
So first, like, as of now, I don't have a model in my head, right? So I don't have a behavioral model, but that's kind of how I'm thinking about it. You're right that I'm thinking about this kind of decision maker and going down that route. I do think, though, that hospitals have strategies in place, right, and anticipate things before the pandemic. So I do think that like ICU departments will have directors, and like emergency departments have directors, and there is some sort of a strategic, like overall overarching management effect. I understand that at the patient level, like who's your doctor is going to matter, right? But at the ICU level, I do think that we can. I do think that I need to do, of course, more research on this, but I do think that this model makes sense. Wouldn't you think so? At the ICU level, because you're not hiring doctors every day.
Right. I guess all I know about this, and obviously we all know that I'm not that kind of doctor, is what I read about in the newspaper, where we hear, like, at least at the day-to-day level, at the very sort of granular level, decisions aren't made from 35,000 feet. They're sort of made at the moment. If somebody is dying, you just kind of take care of them, right? And if they're not, you can sort of smooth it out a little bit better. But it's difficult to say if they can really do that sort of at the level that you think they can. That's all.
Well, I do agree with you, but I think that it's important to make the difference between something like you just said, and we hear on news all the time, which is a patient level outcome, from a hospital level outcome. I do think that when we aggregate all these things, there is less noise, right?
Maybe.
Anyways, yeah, I don't know, Henry. Definitely something to think about. And there are models in health economics about, this kind of hospital level model allocation decision, but you gotta go more deeper in this literature. I think that part of your comment, though, is related to Shauli's comment that we should probably account for the day-to-day variation that you're talking about at the hospital level, which is partially accounted in this model when I have capacity for non-COVID ICU patients, but probably the capacity of COVID patients can influence the outcomes of non-COVID ICUs, right? I don't know, maybe something like that. Gotta think more about it.
We have a question by Marty. Marty, your turn.
Yeah,
Thanks.
sorry. Am I on now? Oh, video. Let me get the video. Yeah, I think by now it's gotten pretty close to what I was going to ask, but I'll say it again because I think it's a slightly different spin on it. Maybe saying some of the same things, but one of them is that in terms of the implications of this, it seems to me like what you've estimated is in addition to the cost of anti-vaxxers on the system, right? There's a spillover negative effect. And I think this is what Mike was getting at when he was talking about wonky morals and stuff like that. This is an additional cost to the system of anti-vaxxers, right? And so that's one way of spinning that. Another way, though, of thinking about this too, is that, 2 days ago, Verna Lau, the head of Alberta Health Services, put an editorial in the paper which says that everybody who's needed an ICU bed has gotten one. But are all ICU beds created equal, especially when you're throwing them into tents and when you don't have doctors and frontline staff to do it too, with the crowding out effect that you're talking about, this limited resources stuff. So you could interrogate a little bit deeper this number of ICU beds and the quality of the service that you get in those numbers of ICU beds whenever the system is being stressed, as that external cost implies, right? So that's just a couple of, yeah, exactly. So it's a couple of ideas about, the implications and why this stuff is important, following up on what Mike and everybody else has been talking about.
No, yeah, I think that it's interesting to have all this discussion about estimation once you go beyond that. So if you get that out of the way, it's just where we started, right? So once you get that out of the way and we can start having more confidence on your estimates, now you can start using them, right? And to the point that Sven made and you were making, others made, that there might be interesting things we can try to do if we believe those estimates.
Okay. Thanks, Bruno. That was great. I was wondering, did you have a discussion with a doctor about your results? In particular, how do you interpret the longer duration of the patients?
Yeah, it's hard to interpret that. Like, we have a draft, we have a working paper for this, and we go definitely in way more detail in what we know from the literature. I haven't found anything in the literature that was as data-driven as this, let's call it that, right? I mean, there are, there is we cite a great piece, editorial letter in Science that is pretty much a doctor writing this letter to the editor, Science issue, speaking to this effect, right, for cancer patients. he talks about his patients are reluctant to come. So my patients are getting diagnosed later, right? I have a non-COVID patients, like, so patients like, you don't feel good. There's the sense that going to a hospital, going to a clinic, you are exposing yourself to COVID, especially in the beginning of the pandemic, which is kind of where we are here in this data set. There is a sense also that there's also a sense also based on this paper and other papers that is more like discussive, right? Offers narratives from a doctor's perspective. There's a sense that patients don't want to get in the way. Look, I got some things, my back's bugging me, but I'm not gonna go to the doctor. They're so busy with the pandemic, kind of thing. So there's a whole bunch of mechanisms from the health demand that can be according to this. And there's the big, also from health production, stretching resources thin, is having to think about a health technology that is completely different, right? Because all of a sudden you have massive need to separate patients. And that didn't really happen before. And I mean, I'm just like, I'm not a doctor, I'm just speculating in my head. But I mean, you read about it, I read about it in this more like letter types of papers. There are a few of those we cite. So that gives us hints to see if we can go into our data set. We do have an interesting data set, right? We have hospital characteristics at the ICU level. So, and we do have also some patient microdata for the patient level. So we'll see what we can do.
Did you have data on the triage rules? Because, I mean, when Henry was saying, well, when someone is not well, we treat him or her, and that's not exactly true. I mean, there is a triage rule, and if the triage is very severe, you don't treat the patient. You actually let her die or let him die, and I guess that this triage rule should have an impact on the way things evolve at the hospital. And if this triage rule are different across hospital, which I'm not sure about that. Maybe it's not true. I mean, they are the same in the same country. I don't know. But if you had difference in the triage rule across hospital, that would be interesting to see if this has an effect.
So my response now to that is, depends on like if you kind of believe what I think it's reasonable, and Henry was more skeptical about like this idea of the hospital level decision making, right? If there's something like that, a lot of it might be captured by fixed effects type of stuff, right? But it is true that we don't have to, like what we have here is ICU hospitalization, right? So you go to the hospital, either straight to ICU or you are hospitalized, get worse, and then evolve to ICU, like there are these stages, right? So we're not getting the guy to go to ER and get a first ER triage. There is some sort of triage or medical recommendation if that patient should not go to ICU. There's some sort of process. And to the extent that there is this hospital level process that influences this, fixed effects will help. To not, then we need more information. One thing that I didn't use, but we do have data on is diagnosis, right? And procedures that were done to this with some aggregation, the aggregation of procedure level. But we do have the procedures that were done at the patient level before the patient went to the ICU and all that. But then our model is not patient level because we don't have a panel of patients. We don't have patient identifier, right? We don't have patient identifier, but we have ICU identifier. So, but if we can somehow translate that, aggregate to the ICU level and see, look, if the disease profiles, and we have like the International Disease Code, right? The CID-10, I think the CID-10 is like a disease code. And that code has meaning, right? So the first two characters are this big group and then goes to finer to like up to the, I think like 10 digits, 12 digits, 10, right? 10. Anyways, so maybe that information gets at what you're saying, like maybe we need to somehow control for the disease profile of that hospital. which is maybe the closest I can get to triage effects. But it's right. We could make a model also on the probability that I need ICU as opposed to ICU outcomes. Right.
Okay. Thanks, Bruno. We are a little bit over time, but it was a nice discussion. I really liked it, and I'm sure everyone liked that. So thank you, Bruno.
Thank you, everyone, for coming. I appreciate it.
Yeah. And so next week, we also have a seminar. Actually, it's me. I present a paper on Friday, so it will be a slightly longer seminar. I try to not to go over time. So that's it for now. Thanks again, Bruno. And
Thank you very much,
see you
everyone.
next week.
Thanks for the comments. I appreciate it a lot.
Yeah, that was very interesting. Very interesting presentation. A bit lost with the details, but bye, everyone.